Good morning, everyone. My name is Dawei, a research assistant at Imperial College London. Due to the virus outbreak, I'm sorry that I have to present this work remotely. Today, I'm going to present our work, explore the effects of local energy markets on electricity retailers and customers. First of all, let me introduce the background and the motivation of this work in slide 2. The decarbonization of power systems have succeeded in addressing the environmental issues. However, this will raise the problem of increasing demand peaks and high availability of renewable energies. Currently, the distributed energy resources, including flexible load, microgenerators, and energy storage, are proposed to support the system balancing and reduce the demand peaks. And the effective coordinating of this large number of small-scale DERs through local energy market has been proposed to addressing the scalability issues, pricing challenges, avoid distributed network reinforcement, and benefit local economics. On the other hand, in deregulated electricity market, this large number of customers or prosumers are represented in the wholesale market by electricity retailers who aim at maximize their own profit but also satisfy the regulatory constraints and the energy balance constraints between retail and wholesale sides. The local energy market is introduced to limit the dependency of customers on the retailer and consequently affect retail's pricing decisions and its economics. Finally, the strategic interaction between these multiple entities will also result in a game theoretical modeling approach. In slide 3, we discuss about the literature review and the contribution of this paper. In the literature, there are many works have investigated the strategic interaction between retailers and individual customers with different types of DERs through single-level and bi-level optimization problems. However, the interaction between retailer and the local energy market integrates all types of DERs and enabling their local energy trading have not been explored. As a result, this paper aims at addressing this knowledge gap and proposes a multi-period bi-level optimization problem that captures the interactions between electricity retailer, independent flexible demand, microgenerators, energy storage, and also a local energy market operation integrating all types of DER. It should be noted that the lower-level optimization problem of a local energy market is non-convex, which cannot be solved by the traditional approach MPEC, where the detailed models are presented in the next step. Finally, the case studies analyze the impact of a local energy market on the energy served by the retailer, retail pricing strategies, retailers, and customer economics. Slide 4 represents the model of the bi-level optimization problem. The upper-level problem represents the strategic decision-making of a retailer who determines the optimal time-specific retail price offered to the customer for buying and selling energy so as to maximize its profit with respect to the regulation constraint imposed on the retail pricing and the energy balance constraint between the retail and the wholesale side. This upper-level problem is subject to 4 lower-level problems. The first 3 represent the decision-making of independent flexible consumers, microgenerators, and energy storage who do not participate in the local energy market and optimize their individual demand generation and storage response to the retail price so as to maximize their own economic surplus. The first lower-level problem represents the operation of a local energy market with different participations, including flexible consumers, microgenerators, and energy storage, which determines the optimal dispatch of these participations and the energy exchange with the retailer so as to maximize their total surplus. Because this fourth lower-level problem is non-convex, as it includes the binary decision variables of the local energy market to either buy or sell energy to the retailer at each Period. The formulated bi-level optimization problem cannot be solved by the traditional approach and converted into MPEG. In this context, this paper employs another approach on slide 5, which is based on the relaxation and the primary due reformulation of the non-convex lower-level problem and the penalization of the associated duality gap. The first step is relaxing the binary constraints as continuous from 0 to 1. Then the convex lower-level problem becomes convex. The second step is getting the dual problem of the relaxed low-level problem. The third step is reducing the bi-level optimizing problem into a single-level optimizing problem by maximizing the retailer's profit, but also minimizing the duality gap of the relaxed lower-level problem, and subject to the upper-level constraints, KKT optimality constraints of convex lower level 1, 2, 3 problems, as well as the constraints of primary and dual problems of lower level 4, and the original binary constraints. The final step is linearizing the single-level optimization problem into a mixed integer quadratic programming by strong duality theory and binary expansion. Slide 6 shows the test system and the examined scenarios in the case study within a single day with hourly restoration. In this paper, the examined retailer serves a set of customers, including 12 aggregated flexible consumers of 3 different types, including residential, commercial, and industrial customers, 6 microgenerators of 3 different types, and 2 identical energy storages. The maximum retail price is assumed to be 250 pounds per megawatt hours. The wholesale market price within the day is assumed to follow the pattern of a typical window day in the UK. In the case studies, there are 3 scenarios, whereas the no local energy market scenario is a benchmark, and all the customers are individually served by the retailer, so there is no local energy market. The small local energy market scenarios means that half of customers, including 6 flexible consumers, 3 microgenerators, and 1 energy storage, participate in local energy market, and the other half is still individually served by the retailer. The large local energy market scenario means that all the customers are participating in local energy market. Next, let's go to the result of this work in slide 7. Which analyzes the impact of a local energy market on the local energy market net demand, the energy storage charging discharging power, which are the top 2 figures, as well as the total demand and the total generation served by the retailers, which are the bottom 2 figures. It can be observed that as the introduction of a local energy market, the net demand and the net generation become higher, which means there is more local trading inside, and the charging and the discharging effects of energy storage become more significant. On the other hand, if there is no local energy market, both total demand and the total generation except the highest values across all the hours, because the only option for the customer to buy and sell energy is through the retailer. If there is a local energy market, both total demand and total generation are reduced because the participating customers have the additional option to trade energy with them and reduce the dependency on the retailer. And this effect is more significant for the large local energy market scenario. The next in slide 8, let's analyze the impact of a local energy market on retailers' buy and sell price, which are on the top 2 figures, as well as the local energy market clearing price, which are on the bottom 2 figures. If there is no local energy market, the strategic retailer exploits the dependency of its customers by offering very high buy price to demanding customers and very low selling price to generating customers. If there is a local energy market, its customers reduce their dependency, and the strategic retailer has to reduce the buy price and increase the sale price to attract higher demand and generation. And this effect is more significant for a large local energy market scenario. On the bottom left figure, we show the relationship between the retail prices and the local energy market clearing price. We found given that the retailer offers a very high buy price and a very low price in the no local energy market scenario, the local energy market participants in the other two scenarios will choose to exercise their option and trade energy at intermediate price, which is a monetary benefit for all the flexible consumers, microgenerators, and energy storages. Finally, it is worth noting that in the small local energy market scenario, and during off-peak periods, the local energy market clearing price are equal to the sale price, which are significantly lower than the buy price at the same period. That benefited for the flexible consumers participate in the local energy market. Similarly, during the peak period, the local energy market clearing price are equal to the buy price, which are significantly higher than the sale price at the same period. That benefit for the microgenerators participate in the local energy market. Having analyzed the fundamental interaction between the retailer and the local energy market, slide 9 analyzes the economic effect of a local energy market on both retailers and the customer. It can be found that as the introduction of a local energy market, retailers' revenue is reduced because the total demand and the buy price are reduced. Retailer cost is reduced because the total generation served by retailer is reduced, although there is a small increase of the selling price. Retailers' net cost in the wholesale market is increased because the reduction of generation is higher than the reduction of demand, so which means the retailer has to buy more energy from the wholesale market. Given about the trends, the overall profit of retailer is reduced. Moving our focus to the customers, both the customers in and outside the local energy market benefit from the local energy market effect. First of all, driven by the reduced buy price and the increased sale price, as well as the intermediate local market clearing price between the buy and the sale price. Finally, let's make the conclusion and the future work of this paper in slide 10. In this paper, we investigate that the local energy market reduces the customer energy dependency on the retailer, limit the price differential of the high buy price and low sale price so as to reduce the retailer's profit but increase customers' benefit. In the future, we aim at model the dynamic interaction between the retailer and the wholesale market and propose a price maker retailer who can act strategically in the wholesale market. We would also like to consider the realistic uncertainties from the customer side in the local energy market operation, and also adopt other approaches such as the stochastic optimization problem and the reinforced learning method to deal with the uncertainties in the market. So finally, thank you very much for your attention, and any comments and questions?
Thank you very much, Dawei.